Okay, looking again at this interesting protein from the coronavirus, we have now explained what these spiral helices are. They're basically columns held together by main chain hydrogen bonds, and we call them alpha helices. That's one type of structure that's used to build proteins. Here's another. You can see these yellow strips. They tend to be straight, sometimes somewhat parallel, and they're indicated as arrows to show their directionality. Let's talk about that on our next video here. So, moving on to the next page, we want to introduce to you the idea of beta sheets. These are sometimes called pleated sheets or extended sheets, and both of these things reflect the reality of the structure. The peptide chain, instead of being curled up in a helix or spiral, is extended. It's as if you pulled it and tried to make it as long as possible. But because it has tetrahedral carbons, it's not going to be perfectly straight. It's going to have a pleated zigzag pattern to it. So, if we take these peptides and stretch them out in this regular repeating pattern, notice we can still have the same type of hydrogen bond that we had before. Main chain NHs and oxygens from carbonyls can form nice straight and strong hydrogen bonds. We've got this set up the exact same way that we had it before. Each stick is going to be a peptide unit like that, and each of these connecting points are the alpha carbons. So we can simply connect these things using hydrogen bonds like we did before. And once again, I'm going to say that we can do this all up and down here. Every carbonyl, every NH is going to be able to form a hydrogen bond, and this forms a nice, strong, solid structure. Now, this is not helical, like we said before. It tends to be a little more flat. And so if we use the analogy that an alpha helix is like a column holding up a building, perhaps this beta sheet, which is flat, maybe we could consider that to be like a wall or a floor of a building. And we have some terminology here to talk about. Each peptide in a beta sheet is called a strand. So this beta sheet has two strands, but we could easily continue this on and do it again. And we could have more hydrogen bonds and have a third strand that continues on like this. Okay, so this would be three strands, and if we put them all together, we end up with this sheet. That's pretty much it. It's very similar in essence to the alpha helix, not in shape, but rather in how it's held together, again, by main chain hydrogen bond repeating over and over again. Okay, what I'd like to do now is go down toward the bottom of the page and point out that we can have two different types of strand interactions in beta sheets, and they're both about the same stability, and they're both found in about equal numbers. Let's acknowledge that each strand has a directionality. All peptides do, and we can put an arrow onto a strand showing the area of, say, two strands where they are hydrogen bonded to each other like this. Now, in one case, we would have two strands that are technically parallel to each other geometrically, but they're going in opposite directions. And you can imagine that we could have something curving around like this to connect them, and you would have a nice continuous structure. This is called an anti-parallel beta sheet interaction or beta strand interaction. It's parallel in the sense that it's geometrically parallel, but it's anti because they go in opposite directions. The other type is simply called parallel, not anti-parallel, but just parallel because, again, the strands are going in parallel to each other, but they're actually going in the same direction. Now, I hope you'll recognize something here, and that is we cannot, don't draw what I'm going to draw here because you can't do it. We cannot draw a connection like that. You can't have two heads of arrows coming toward each other. The strands have to go in the same direction continuously as you go through the peptide train. So let's get rid of all that, and let's point out that we would have to connect these two strands. If they were indeed directly connected, we'd have to do it by some other means like this, so that we could say if this is the amino terminus here, we're going to follow through this strand, come around, and follow through in the same direction until we get to the C terminus. Over here, on the other hand, with the anti-parallel, you have the N, and it comes and goes around, and you could have the C terminus right here. So I want to tell you that you can have anti-parallel and parallel strand interactions in the same protein. In fact, you can have them in the same sheet. So we're going to see examples of that a little bit later. Okay, one more thing before we leave the beta sheets behind. I think we can do this all in one video. Let's consider again that what we have shown up here at the top of the page is simply the main chain. We're not showing the side chains. In order to understand the side chains, we have to flip this main chain sheet on its side and look edge on like we have it down here. It's the same sheet. And what we can do now is recognize that, again, the R groups are going to be connected to the vertices between sticks because they are connected to the alpha carbons. And I want you to notice the pattern of the R groups or the side chains. The first side chain here is going above the sheet. The next one is below, above, below, above, below. And that's worth a little note here, and that is that side chains alternate one side to the other of the sheet. Now, we're going to make use of that fact as well. Probably try to do that in class to talk about how you could take a sheet, or like I said, it's like a wall in a building, and you could sort of paint one side with a particular type of functionality of side chain, and you could paint the other side or cover the other side with different types of functionalities. That'll be a useful fact for us to know, and what we have here now is, I think, pretty much good enough for understanding beta sheet.